We will come to which one is correct in a moment. Next, I want you to write the electron configurations for the following atoms using noble gas notation. You wrote the complete electron configurations for these 4 atoms moments ago. Now, what you will do is take the part that belongs to the nearest noble gas. So for example, in phosphorus, 1s2, 2s2, 2p6 is the same electron configuration as neon. So replace this entire part of the electron configuration with neon in brackets, like this. You can do the same for titanium and chromium, replacing 1s2, 2s2, 2p6, 3s2, 3p6 with argon in brackets. You need to remember the brackets. And then just write the electron configuration for the valence electrons. 4s2, 3d2 for titanium, or for chromium, remember there's 2 possibilities, 4s2, 3d4, or 4s1, 3d5. For praseodymium, the electron configuration is going to be xenon, 6s2, 4f3, or xenon, 6s2, 5d1, 4f2. Now we've looked at 2 possible exceptions to the trend that we've talked about in electron configurations, chromium and praseodymium. Let's focus on chromium. For Cr, is the correct electron configuration this or this? It's been found experimentally that the correct electron configuration is this, because energetically there is very little difference in energy between the 4s and 3d orbitals. The electron-electron repulsions that come from pairing up electrons in the 4s orbital contributes to the pairing energy. What is preferred is to have 6 unpaired electrons in the 4s and 3d orbitals instead of having a pair of electrons in the 4s and 4 unpaired electrons in the 3d. Now, by having a half-filled 4s and 3d orbitals, the electron configuration is more stable than having a completely full 4s subshell and a partially filled 3d orbitals. There are other exceptions as well. For example, copper has an electron configuration of argon 4s1 3d10. Molybdenum has an electron configuration of 5s1 4d10. And there are a number of lanthanides and actinides, so praseodymium is an actinide that has unusual electron configurations. On a test, I might try to confuse you with something like chromium, copper, or molybdenum, but I won't try to trick you with an actinide or lanthanide. Next, we need to talk about the state of the electrons in the atom. There's 2 possible states, ground state and excited state. The definition for ground state is the lowest energy state of a system. The orbitals in atoms are filled using electrons in order of increasing energy, and the lowest energy orbitals are filled first. Remember that E- is electrons. So for example, when looking at 1s2, 2s2, 2p2, all 6 electrons are in the lowest possible set of orbitals, and that is the ground state electron configuration for carbon. An excited state is the state that has higher energy than the ground state. So this would be like light coming in and striking a carbon atom, exciting one electron from the 2p orbitals to the 3s orbitals. Next, let's talk about writing electron configurations for ions. When we want to form ions, atoms either gain or lose electrons to have electron configuration similar to the nearest noble gas. So, let's think about oxygen. Oxygen has an atomic electron configuration of 1s2, 2s2, 2p4. The nearest noble gas to oxygen is neon. So oxygen needs to gain 2 electrons to form O2-. The electron configuration for O2- is 1s2, 2s2, 2p6. Calcium. It has an atomic electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Its nearest noble gas is argon. So calcium should lose 2 electrons to form calcium 2+, which has an electron configuration equal to argon. When you write electron configurations for transition metal cations, the rule is to remove electrons from the s orbitals first. So, when looking at vanadium, atomic vanadium has an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d3. To write the electron configuration for V2+, first you remove the 4s electrons first. So V2+ has an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 3d3. Now, let's talk about an idea that's going to be very important for the next lecture. It's called shielding, or it's also known as screening. The variable associated with shielding is the capital S. And what happens is the core electrons reduce the force of attraction between the nucleus and the outer electrons. So what happens is that the core electrons, the innermost, it blocks part of the charge that the outer electrons see from the nucleus. This reduced amount of nuclear charge on the outermost electrons in an atom or an ion is known as the effective nuclear charge. We're going to calculate the effective nuclear charge for atoms and ions.